Continuing in section 9.7 on our in-class worksheet, I now want to talk about logarithmic equations. So when we solve logarithmic equations, we're determining the domain of the variable of the equation, and we're going to use properties of logarithms to combine all logarithms and write as a single logarithm if needed. We're going to eliminate the logarithm by rewriting the equation in exponential form. We're going to solve for the given variable. We're going to check for any extraneous solutions. Now here in solving logarithmic equations, the check is required. And we're going to verify that each solution is in the domain of the variable. So one of the things we'll need is to review the properties of logarithms. Remember, b is bigger than 0 and different from 1. U and v represent positive numbers and r is any real number. If those are satisfied, then the base b log of u times v is the base b log of u plus the base b log of v. This is the product rule for logarithms. The base b log of u over v is the base b log of u minus the base b log of v. That's the quotient rule for logarithms. The base b log of u to the r power is the same as r times the base b log of u. That's the power rule for logarithms. So let's look at an example. If I have the base 4 log of 2x minus 1 equals 2, then the domain of the variable is all x bigger than 1/2. I obtain that by setting 2x minus 1 greater than 0 and solving, because this input to any logarithm has to be bigger than 0. So when we solve 2x minus 1 greater than 0, when we simplify that, we find out that x needs to be greater than 1/2. So whenever we get a solution, we have to make sure that any solution we get is bigger than 1/2. If it's not, we have to reject the solution. So we're going to take this log equation and write it in exponential form. The base of the log is the base of our exponential. The log is the exponent, so the exponent is 2. So I apply 2 to the base of 4, and the result is whatever is in the input position of my log. So the result is that 4 squared needs to equal 2x minus 1. 16 equals 2x minus 1. 17 equals 2x. X has to be 17 over 2. And because that is bigger than 1/2, the solution satisfies the inequality, so we don't have any extraneous solutions. And we can verify the solution by substituting it into the original equation. And we will obtain a true statement. So let's look at solving the logarithmic equation base 4 log of x plus 1 equals to base 4 log of 6x minus 5. Now we have a couple of ways we can solve this, but the easiest way to solve this, since there is exactly one base 4 log on the left, exactly one base 4 log on the right of the equals, is to merely set the inputs x plus 1 and 6x minus 5 equal to each other. That's the only way this is going to be true, since the logarithmic function is a one-to-one function. If two logs equal, their inputs equal. So solving this, let's subtract x from both sides. And let's add 5 to both sides. So we wind up with 6. These cancel out and these cancel out, equals to 5x. Dividing both sides by 5, x equals to 6/5. And so notice that I didn't find the domain of this function to start with. Another way that I can do this problem is just to check my solutions instead of finding the domain at the beginning. Alright, so this is a proposed solution. So we have the base 4 log of x plus 1, that's 6/5 plus 1, equals the base 4 log of 6 times 6/5 minus 1. So this is how I would check. So 6/5 plus 1 is actually 6/5 plus 5/5. I can rewrite 1 as 5/5. And 6 times 6/5 minus 1 Okay, so on the left we have the base 4 log of 11/5. And on the right, let's see here. Oh, and here I copied this wrong. This is minus 5, so that's the problem. This is a minus 5. So 5/1 times 5/5 is 25/5. And notice that does equal the base 4 log of 11/5. So that is correct. So that basically tells me I was replacing all x's with 6/5. So that tells me x equal to 6/5 really is the solution. Okay, so now we're going to look at a log equation where we have more than 2 logs involved. So the first thing we want to do is to take this left side and write it as a single logarithm. So first I'm going to use the power property for logs. This 2 multiplied by the base 5 log of 3 minus x becomes an exponent. And I now get the base 5 log of 3 minus x to the second power minus the base 5 log of 2 equals the base 5 log of 18. Alright, so I'm now, because of this subtraction between these 2 logs on the left, I can use the quotient property. The base 5 log of the square of 3 minus x divided by 2 equals the base 5 log of 18. And at this point, I have exactly one logarithm on the left, exactly one logarithm on the right. I can actually set the inputs equal to each other. The only way these two logs are going to equal is if what's inside of them equals. So the square of 3 minus x over 2 has to equal to 18. And then I will multiply both sides of this by 2. So here I'm using the equality property of logarithms. So these divide out, and on the left I'm left with the square of 3 minus x, and on the right I have 36. So the square root property tells me that I can lose this exponent of 2 on the 3 minus x if I apply plus or minus square root to whatever is on the right. So I now on the left simply have 3 minus x. On the right I have plus or minus square root of 36. So 3 minus x is plus or minus 6. So to solve that, I'm going to subtract 3 from both sides of this. So I'm subtracting 3 from the left and 3 from the right. So negative x is equal to, and I can put that in front. Probably the typical way that you'll see this is it would be in front of this. So minus 3 plus or minus 6. So negative x is minus 3 minus 6, or negative x is minus 3 plus 6. So negative x is minus 9. If I multiply both sides by negative 1, I get x equals 9. Or minus x is 3. Multiplying both sides by negative 1, x is minus 3. So x is either 9 or minus 3. Now, remember, I can either find the domain of the equation, or I can just check to make sure that this doesn't give me anything undefined. So the original equation is what I want to go back to. So I want to go back to this and replace all x's with 9. So this is my check. So 2 times the base 5 log of 3 minus 9. And I can stop right there. Minus, I'll just put dot, dot, dot. No need for me to go on, because I see that I'm taking the log of a negative. And that's, the input to a log must be a positive number. It can't be 0, it can't be negative. So this is undefined. So basically, that tells me x does not equal to 9. I was letting x equal 9 here. I got an undefined expression. I stop as soon as that happens, and I know that x can't equal the value I was checking. All right, let's put in negative 3. 2 times the base 5 log of 3 minus negative 3 minus the base 5 log of 2 needs to equal the base 5 log of 18. So we have 2 times the base 5 log of 6 minus the base 5 log of 2 needs to equal the base 5 log of 18. Well, let's use our power rule, which says 2 times the base 5 log of 6 is the base 5 log of 6 squared. So we want to get this left side down to a single logarithm. So this is the base 5 log of 36. And since this is being subtracted, this base 5 log of 2 is subtracted, the quotient rule of log says I can make one base 5 log and make the 2 from the log I was subtracting the quotient of the 6 squared, or the 36. And so we know that 36 over 2 is 18. So we see that these two are equal to each other. So this does check out. And that basically tells me that x equal -3 is my solution. That's what I was checking. So that does solve this equation. Another type of equation that shows up is an equation where not everything, so the previous equations, the only terms in the equation were logarithms. Here we have 2 logarithms and a constant. So we want to take and use the product property of logarithms for this left side. So this is, we want to get a single logarithm on the left side. So this is the base 2 log of x minus 2 times x plus 2. That's what the the product property of logarithms would tell us. So this is the base 2 log. X minus 2 times x plus 2 is x squared minus 4. That's a difference of squares. So now what I do when I have a logarithm that involves a constant and logs, I get a single logarithm on one side of the equation, the constant on the other side, and now I'm going to translate this into an exponential equation. If the base 2 log of x squared minus 4 is 5, then that means 2 to the 5th has to equal x squared minus 4. So this is 32 equal x squared minus 4. So let's add a 4 to both sides. And we have 36 equals x squared. And remember, I can apply the square root property, which says I can lose this exponent of 2 on the x if I apply plus or minus square root to the 36. So I can always use the square root property when I have something being squared on one side of the equation and a constant on the other side. So plus or minus 6 is equal to x. And remember, we have to go back to the original equation. So let's go back to our original equation here. And let's check. All right, so let's let x equal to 6. I get the base 2 log of 6 minus 2, that's 4, plus the base 2 log of 6 plus 2, that's 8, equals 5. Well, the base 2 log of 4 is the exponent I apply to 2 to get 4. That's 2. The base 2 log of 8 is the exponent I apply to 2 to get 8. That's 3. 2 plus 3 is 5. So we see that that actually works. This tells me that x does indeed equal to 6. Now let's check x equal to negative 6. And we see when we do that, we get the base 2 log of negative 6 minus 2. That's negative 8. There's no need for us to go on. As soon as we get something that's undefined, we cannot take the log of 0 or the log of a negative. This is, if you put this in your calculator, this is undefined. So we stop right here, and we know that x therefore does not equal negative 6. So our solution set only includes the positive 6. All right, so this check right here basically tells us that x can't be negative 6. So if you were given a solution set for this, you would just write the set with a 6 in it. If you were telling what x equals, you would have to make sure you've made it clear that x only equals the positive 6.